Hi there, my name is Daniel, and for my EECS 203 video, I'd like to show you a proof from the homework set. So the proof is as such, the problem is as such. Given a relationship R over the set A, we want to prove that R is transitive if and only if R squared, or R composed with R, is a subset of R. So the topics in this question are, first of all, if and only if proofs, because we have if and only if here. Then we have relation properties, because we have this keyword here, R is transitive, transitive is a relation property. 3 is set proofs. You may be asking yourself, where are the sets here? Well, remember, relations are also sets. There's 3 representations of each relation, right? There's the graph representation, which is visual, then matrix representation, and finally there's the set representation. So relationships are actually sets. And that's why we're able to say that R squared is a subset of R. And finally, composition of relations, because we have here R squared, R composed with itself, and so that's the final topic. So for our proof strategy, since this is an if and only if proof, if you recall from our logic unit, P if and only if Q is the same thing as P implying Q and Q implying P. So if we can show that if R is transitive, then R squared has to be a subset of R, as well as another claim that if R squared is a subset of R, then R is transitive, then we can conclude this, and our proof will be complete. All right, let's get started. So the first thing that we want to do is we want to show the first one. So the first proposition, or first mini proof, we want to show that if R is transitive, then R squared must be a subset of R. So how can we go about doing that? How can we show that R squared has to be a subset of R? Well, the definition of subset means that if there's an element in R squared, it must also be in R. So if we assume an arbitrary element in R squared, and using our assumption that R is transitive, we can show that that element in R squared is also in R, then we can successfully prove that R squared is a subset of R. So we'll assume an arbitrary element, this pair xy in R squared. Then, by the definition of relation composition, there must exist an element z subset of R such that x are z and z are y, right? That's just the pure definition of relationship composition. And finally, by the definition of transitive property, since we know that x are z and z are y, since we know both of these, that means that x are y, right? That's just a pure transitive property. If you don't quite remember that, do review your notes. But yeah, since we have these 3 things, and the first maps to the second, and the second maps to the third, then the first maps to the third. Therefore, since we have x r z, we know that x z is also in R, right? So we've proven that we have this arbitrary pair inside of R squared, and that arbitrary pair must also be in R. Therefore, R squared is a subset of R. All right, we're halfway there. Here's the second half. We want to show the vice versa now. We're going to assume that R squared is a subset of R, and we want to prove or show that R has to be transitive. So how can we do this? Transitive property means that given that, what I just said, right? You're going to assume that the first thing maps to the second, and the second maps to the third, and you're going to want to show that the first thing maps to the third. Cool. So we're going to assume x, y, and z inside of set A, and we're going to assume that the first thing maps to the second, so x maps to R, x maps to y over R, and the second thing maps to the third, so y maps to z over R. And we want to show that the first thing maps to the third, so that x maps to z. So if you remember the definition of relationship powering or composition, you'll see that right here, if we have A R B and B R C, that means that A maps to C over R squared, under R squared. So we have the 2 assumptions, right, that x are y and y are z. So therefore, we know that x are squared to z, right? So we can conclude this. Okay, what can we do with this piece of information? Well, we know that R squared is a subset of R. So if x, xz is an element of R squared, that means that xz must also be an element of R. Therefore, we have shown that xz is an element of R, and we have shown that R is transitive, and our proof is complete. Since we have shown that if R is transitive, then R squared is a subset of R, and if R squared is a subset of R, then R is transitive. Thank you for listening to my video, and I hope you learned something. Goodbye.